So thank you first of all for coming. So I know that the first session on a Sunday morning after conference dinner is always tough for all participants. So thank you very much for coming. So yesterday evening we wanted to convince Wolfgang to start 1 hour later, basically, but he was not convinced about this idea. So, but then finally it turned out that we can that we have 1 hour more this night. So effectively it's 10 o'clock. So that's fine. Okay, so my talk is about surprises, basically, but not those kind of surprises we faced yesterday evening. So when about losing a propeller, and a dynamically planned conference dinner turned out to be rather static. So here I'm talking about these kind of surprises where we know that something will happen, and we exactly know when it will happen, but we do not know exactly what will happen. So like this talk, right? Okay, so this is joint work with Dieter Hess from the University of Cologne. So he's a financial economist, or not an econometrician, and David Veredas from Brussels. Okay, so what we are talking about? We are talking about one of the most fundamental questions in financial economics: how is fundamental information incorporated in financial prices? We know this is very important for price discovery, the study of market efficiency in accounting and corporate finance. A lot of research has been done already, so we are, of course, by far not the first studying this question. So we know a lot about the direct price impact, so how fast do prices react on news announcements. Only a little research has been done on liquidity impact, so there's only one study in the Journal of Finance, so basically based on descriptive statistics. So there should be done much more on the effect on liquidity, actually. And some work has been done regarding the volatility around announcements. So some papers by Torben Andersen and Tim Bollerslev, and some work of ourselves. And finally, quite recent work has been done on studying the precision of announcements. So where we're talking about the quality of an announcement and how market participants interpret new information. Okay, so this study in some sense combines these different aspects. So this is a study on high frequency data. We are studying the ask, bid, quote process around macroeconomic announcements. And so this is not a very technical talk, so don't have too high expectations with respect to the technical level. The model is rather simple, so it's more an empirical talk, based on a lot of data and a lot of figures and graphs, finally. So the idea is rather simple. We will decompose the quote returns into an efficient return. So one component which we call the efficient return, the unobservable efficient return, and some idiosyncratic noise terms. And correspondingly, we will decompose the conditional return volatility into an informational volatility, which is related to the efficient return, and to noisy, basically liquidity-induced volatility. I will explain in more detail what it actually means. Okay, and then we will study these different components around announcements also, and we will use a measure in order to estimate the precision or to predict the precision of news. And we will study, okay, what does this mean for volatility and liquidity around news announcements? So the objective and research questions are actually three fundamental questions. So how strong is the impact of news on these informational and noisy components of volatility? And how does the proportion of these components, in particular the proportion of noise in conditional quote return variances, behave before and after announcements? And finally, do these impacts also depend on the precision of news? So in this sense, this study contributes to several strengths in the literature. Well, I will come back to that. I will explain this. So we will contribute to several strengths in the literature. The impact of announcements on prices and volatilities, the role of information precision, which is a rather new string, and the literature on price formation based on high frequency data. So basically our model can be seen as an extension of the model by Engel and Patton. And the role of noise in realized volatility modeling. So this is not a realized volatility talk, but okay, we will talk about market microstructure noise. And this plays an important role in realized vola literature. So the outline of the talk is I will present you a rather simple state space model for ask and bit log returns with corresponding conditional variances. We will have a brief look on the data before I will explain you in more detail how we measure the precision of news. I will talk a little bit about the estimation of the model, which is theoretically straightforward but practically not straightforward. So here we suggest a two-step procedure actually, and then finally I will show you empirical results. Okay, so how does this state space model look like? We have ask and bit quote log returns, so a two-dimensional process, so that's for ask, and bit quote. So this is what we can observe in the market. What we cannot observe is the so-called efficient price, well, which is probably somewhere in between. This is what we cannot observe. So we try to make this observable or to estimate it by using such a state space model where we model this return process, this bivariate process, in terms of a vector of state variables, of latent variables. So this is this SA is related to the noise on the ask side of the market, the noise on the bid side of the market, and M is related to the efficient return. So this matrix H here basically you see, okay, that the ask return is then basically the sum of the ask noise component and the efficient return, and the bid return is basically the sum of the bid noise component and the efficient return. So it's a rather simple structure.
What do I have to understand under T? Because
T is we will, yes, that's true, but we will use later on, we will use equidistant data, we will use 1 minute or 2 minute data, we will aggregate. Yeah, okay. So this is the idea. Yeah? So, and this ask and bit noise, basically what does it mean? So when it is 0, then this means that ask and bit quotes, they move in locksteps. That means the spread in the market is constant, and they are perfectly co-integrated, and so there is no deviation between the movements in the efficient return and the quote returns which we can observe. So then we impose some latent factor dynamics. Here's also a rather simple model, so in forms of a VAR1 process for this vector of latent variables, with some constant vector where we assume that, okay, the mean or the constant parameter for the noise terms is equal to 0. I think this is a fairly acceptable assumption. And of course, then we allow for some drift in the efficient return. But we will see that this, for our analysis, that's not too important. Then this matrix F is the matrix of the autoregressive parameter, which can be arbitrarily parameterized, can be fully parameterized. As we will see in our later study, the most important components basically are these diagonal components. Yeah? Okay, and then of course we have some error term and with some time-varying covariance matrix. And well, what we allow in the moment to have time-varying diagonal elements, so we're mostly interested in the variances. And okay, we also could generalize the model in order to allow for time-varying correlation. This could be done in this step. It's not a big issue, but it's not of the crucial interest here. Okay, so and then finally, well, alternatively, well, this is maybe what I forgot to explain here. We also have some regressors in the return equation. What are these regressors? I will also explain this later on. These are basically regressors capturing the impact of news. That means the type of news, the sign, and the magnitude of news. And well, this could be also, alternatively, could be also included here in this dynamic equation here. But well, then identification can be tricky because it depends on the dynamics and the model. So we decided to do it directly in the observation equation. Yeah.
Did we think about NT as something that is observable?
No, it's unobservable. Everything is unobservable. All three components are unobservable. This is the efficient. What would be observable?
The bid and ask side would be observable.
Yes, what we observe is the best ask and the best bid, right? So the time series of best ask and best bid. So returns computed for these time series. This is what we can observe. This is our so-called quote log return. Yeah? But it might happen that the efficient return is somewhere in between. Yeah? This is what we cannot observe. This is what we try to identify here.
Similar naive question, why does the efficient price not depend on the news?
It depends. It depends. Of course.
I thought you observe the ask. Could you go
No, sure. It depends. Well, this is the
R depends, but the M does not depend on the X.
oh, it does. It does because well, this is the observe. This is the ask return, and this is the bit return. It depends on use. So, yes.
M depend on X?
Sure, implicitly, because we're assuming that. So, what is R? R is the sum of SA and S and M. So this gives RA. So the sum of both depends on the news. Yeah. Okay.
I assume that in this R series you have many zeros. That's why I just guess it because if T is a very small
Yes.
time level, that means it's a model.
Yeah.
It doesn't make sense to me because it's a linear model. You should rather think of a generalized linear model where you have a logic term or so that.
Yeah.
I don't understand the linear structure. It comes out of the blue, or it falls from the sky, they say in Germany.
No, it does not fall from the sky. Well, this is a model.
Other people did it, or that's why you use it?
This is a fairly standard model, which is also used, has been used by other people in literature, which is used in the realized volatility literature. And here we use it for 2-minute returns, for 1-minute returns. So we don't have these problems, which you probably have in mind when we really go on the transaction level. Then I would fully agree with you. But I think for 1 and 2 minute, and we are studying a very liquid asset. So there, this problem, what you don't have in mind, is not as severe.
You study a very liquid asset at a very coarse time scale, then it works.
Yeah.
Okay.
Exactly.
If you study a less liquid asset on a very fine time scale, you will not use this model.
Sure, I fully agree.
I understand that was
Yeah, yeah.
just about T's.
Absolutely. Yeah, sure.
Things clear.
Yeah. Okay, good. So this is a model, so going just back, this is a model for ask and bid returns. And then, of course, this means we implicitly also have a model for spreads, the spread dynamics, because we can easily rotate the model. So just multiplying this vector here with this rotation matrix. And then what we get is basically a model which describes us the changes in the spread and the changes in the mid-quote. And the mid-quote is the average of the ask and the bid. Okay? And this is in the standard literature. This is typically used as a proxy for the efficient return. Which is typically not too bad. But it very much depends on the liquidity of the aspect, in particular around news announcements. This might be a bad proxy. Okay, good. We can compute some reduced forms of the model. That's not too important. I do not want to lose too much time on that. What is more important are these variances. So we're mostly interested in the conditional variances. And when we impose that only the diagonal elements of our covariance matrix are time varying, then we can say that the conditional variance of the ask and the bid return is at least proportional to, this is the variance of the efficient return, this is the variance of the efficient return and the variance of the ask and bid noise. So in the following, we will describe this as the noisy variance components and this as the informational volatility component because it is related to the efficient return. Yeah? Okay, and then of course this model also means that the covariance then is just straightforwardly described by the variance of this informational volatility. And well, what is most interesting then later on in the empirical analysis is to analyze variance shares. So what is the proportion of noise in the total ask variance? So the noisy share, and this is the total ask variance or bid variance. So here we get a straightforward measure for the noise proportion. Yeah? So alternatively, you also can compute, okay, what is the noise, the ask share or the noise of ask, the share of ask noise relative to the bid noise. So is there an imbalance between ask and bid noise around announcements, and maybe does this also depend on the sign of the announcements, whether we get positive or negative surprises? Okay, I will come back to that. Okay, before we continue, let me briefly explain which data we use because this is quite crucial. So Wolfgang's questions have been already related to that. We will study transaction data, so aggregated transaction data, 1-minute and 2-minute returns of the Bund future contract. So why do we use the Bund future? First of all, it is the most liquid, or maybe in competition with the US T-bond future, among the most liquid future contracts in the world. Yeah? So a very liquid asset. And well, why is this interesting database for our study? Well, because as you will see, maybe I will jump back to this slide, but just to give you the idea, we will match this with announcement data of macroeconomic announcements from the US, basically news announcements on non-farm payrolls, the non-farm payroll figure, and the unemployment rate. So it is well documented in the literature that these are the two most influential macroeconomic news we can observe. Yeah? And we know very well, it has been documented in a lot of paper, that markets, in particular the T-bond future and also the German Bund future, they react very, very strong on these announcements. Yeah? So this was our idea. And why do we use the German data, not the US data? Because here we have more information. First of all, we know that the most influential announcement for the German Bund future is also the US labor market report. And secondly, we have more information in this data because we have the quotes, we also have volumes, we have a broader database. This is the reason. We have a sample period from 1995 to 2005, and we focus only on announcement days of the US employment report, so we do not want to any interference with other announcements. So we want to be very sure that this announcement is the only news coming on the market. And then we end up with 123 employment report days. Okay, so, well, non-farm payroll figure in the unemployment rate, the non-farm payroll figure, this is the news job outside agricultural sector, which comes from the establishment survey, and the unemployment rate, which is of course they are closely connected, but they provide independent piece of information. Yeah? This is also documented in the literature, and we did some work on that already, so it's absolutely reasonable to include both figures because the unemployment rate comes from the household survey. So we really have different sources of information. Well, and since we know that that only the non-anticipated information, that means the surprises, they drive financial markets, so it's very important also to know, okay, what do markets expect on these announcements? So we have survey data on analysts' forecasts based on the former MMS, and meantime it's called Informa Global Markets. So these publicly available surveys from analyst forecasts with respect to these announcements. Yeah? So that means we end up with the surprise, the non-anticipated piece of information, which is the announced number minus the forecast. Okay, so very briefly, I do not have too much time, very briefly, how do we measure the precision of news? Our basic idea is a rather standard Bayesian learning model where we assume we have some prior beliefs on some fundamental variable X, which is maybe the unemployment rate. So we build some expectations on that. So we have mu F. So for instance, this is the mean forecast, therefore F, the mean forecast on the unemployment rate. And well, so this is this Bayesian notation. So then rho is the precision, the inverse of the variance. Yeah? So then we get some noisy estimate of X. So this is our news announcement coming on the market. So A stands for announcement. So it's a noisy estimate of the true unobservable macroeconomic figure. And well, we assume that, okay, in average we are right, but okay, we have some uncertainty, yeah, which is captured by this rho A, the precision of the announcement. Then when we put it together using a Bayesian updating, we get the posterior beliefs. That means the conditional distribution of X given the announcement. And well, then it's a fairly straightforward result that then the mean of this distribution is just the weighted average of our forecast and the announcement. Yeah? And this pi here is the so-called price response coefficient, which is the ratio between the precision of the announcement and the total precision of the forecast and the announcement. So, and this is what we use in order to measure precision. And now, of course, the crucial question is, how can we estimate this? And this is done, has been done based on some previous work where we suggest to extract some detailed information from macroeconomic announcements in order to measure the precision of information. First of all, the precision of the forecast is, and this has been done by other people already as well, is straightforwardly estimated based on the cross-sectional variance of analysts' forecasts. I think this is a very valid measure in order to get an idea of the cross-sectional dispersion of expectations. Yeah? Okay, I think that's not a problem. That's a very reliable measure. But the question, okay, how to measure the precision of an announcement? There is no information provided in the employment report which tells us, okay, this is a precise, so this is a very valid figure, or it's a non-valid figure. So this is somewhat tricky. And well, we realized that there is more information in the employment report as it is typically exploited in empirical work, namely the revisions in non-farm payrolls. So the non-farm payroll is the most important figure, most important and macroeconomic figure we can think of. So in some papers it's referred to the king of announcements. So this is quite crucial also to think about revisions and, well, the precision of these announcements. Well, and there is some, why are there revisions? Because there is incorporation of late responses or follow-up inquiries with non-respondents. There's re-estimation of seasonal adjustment factors, and there's also seasonalities in sampling precision, because during the summer months, labor market entries of students, for instance, it's much harder to estimate non-farm payrolls. Okay, so when we just look on the time series of these non-farm payroll revisions from 80 to 2002, well, we have it until 2005 in meantime, well, then you see some regularity, and the regularity is mainly related to the absolute surprises. So that means the second moments, but not to the first moments. And well, in order to capture this and in order to analyze whether there is some predictability in these non-farm payrolls, because, well, this is what I forgot to tell you, this non-farm payroll figure, it is published together with the announced figure, but it is always related to the previous month's figure. That means you get, at this month, you get the non-farm payrolls figure for the last month together with the revision of the figure 2 months ago. Yeah? So that means we try to exploit predictability in the second moments of the non-farm payrolls in order to get a forecast for precision. This is what we are doing here. I do not want to go into much detail. So basically we use a kind of armor-gauge style model with some seasonality component in order to predict the news precision. Yeah? What do we find? We find there is no predictability at all on first moments. Yeah? So that means the revision itself is not predictable, which is good news for the Bureau of Labor Market Statistics in the US, because otherwise they would do a rather bad job, because if there would be predictability in the revisions, then they should include it directly in the figure. Yeah? But we found predictability in the second moments. Yes?
Why do you have to invest so much energy into determining the variation of your news? That's what you are doing here. Why
Yes.
do you use this Bayesian approach? Is it really so important to get precise news? Can't you just take the farm roll announcements as such? I mean, for the later you are interested in your coefficients B and
Yeah.
H, sorry, F or whatever.
Well,
your coefficients there. And will they vary so much? I mean, it seems to be that you spend a lot of energy on something that may not, in a more engineering type of approach, may not play a role.
oh, it plays a role. It plays a role. So in this paper, so this is wrong, this is 2007 by the way, in this JFQA paper, we show that it matters. It matters in the sense that markets react much more sharp to precise. When they think the news is precise, they react much more sharply than when they think that this is imprecise, non-valid news. When they think, okay, there's a high sampling errors. So it matters. It matters in order to describe market reactions to, so it's not only important the magnitude of news and the sign of the surprise, it is also important to get an idea, okay, how reliable is this measure? Yeah? And from a Bayesian point of view, from a Bayesian updating framework point of view, it totally makes sense. Yeah? Okay, but that's not the main story. So therefore, I do not want to spend too much time this. We use this precision measure later on, but I want briefly explain so how we estimated it. Yeah? So then when we put it together, we get an estimate of this price response coefficient.
Goes into the same direction of Volodya's question yesterday. Can't you incorporate this mechanism, because this also falls out of the sky, this basically armor-gauge model to dream up this row ahead. You just dream it up as an armor-gauge model. Somebody else dreams it up as a different model.
True.
So can't you just take this dreaming up procedure into your linear system directly? because you
No.
precisely said people react on the precision of the news, and this is your precision. This is the basic.
Right.
But yeah, that means this element of your model could be another component in your state space.
No, because this is based on monthly data. Monthly data based on the news announcement. The state space model, which is in 2-minute returns. Well, we can do this, but then we have millions of data points. Actually, we consider 2-minute returns and a quite narrow window around the announcement. And the announcement is on a monthly basis. So we really have fundamental different time scales. Otherwise, you would be perfectly right and would be much more elegant and convenient. I fully agree with that. Okay, so let's keep the economic arguments a little bit on the estimation. So what is the problem here? So estimation, in the moment, it's rather straightforward. So what we could do is a quasi-maximum likelihood interpretation and using the Kalman filter in order to estimate the state space model. Also with the parameterization of the conditional variances. So theoretically possible, but the problem, it turns out that we have to parameterize these conditional variances in a relatively flexible way. And this is also what our empirical results show us. So the simultaneous modeling of the first and the second moments in this state space model is computationally, numerically very cumbersome. I spent a lot of time on that try to estimate it, and basically then I decided, okay, let's switch to a two-step procedure where in the first step we consistently estimate the parameters of the model using QMLE Kalman filter. Then using the updated Kalman filter estimates of the latent errors as so-called generalized residuals, and then doing our variance analysis based on these squared generalized residuals in a second step. Yeah. So, so how much time do I have left, Volodya?
It was started a little bit later, but so I mean 15 minutes at least.
Okay, okay. So I'm too fast. Okay, okay. So the, but I have many figures still to show. So, okay. So so the idea is to augment the state space system basically, and to treat these unobservable errors here as latent factors. So this is straightforward, a well-known approach, also suggested by Harvey. So that means, okay, then we have 3 additional latent factors. And the 3 additional latent factors is these unobservable errors. Okay, there we allow some, okay, in the moment it's a diagonal specification. We also could allow 4 time varying elements here. That's not the main issue. The most interesting elements are these covariance, these variance elements. So the Kalman filter then yields us either updated or also smoothed estimates of our latent errors, and this is what we, well, that's a general expectation, the conditional expectation of our latent error given the current information set, what we define as a generalized residual. Yeah. So then we do our second step, that means the modeling, the parameterization of the conditional variances of these 3 components in terms of, yeah, effectively it's a VAR model, so effectively it's a multivariate gauge model. Yeah? So a gauge model, well, as we just yesterday discussed, well, it's just nothing else than an ARMA model based on squares. So this is a VAR model based on squares, effectively, where we include here some announcement variables, which I will describe in the following. So this is a rather straightforward way to parameterize that. Okay, so the empirical analysis, we focus on these announcement days only. So we focus on the whole announcement days, so it starts at 8 o'clock to 5:30 Frankfurt time when future trading. The US announcement is scheduled at 2:30 Frankfurt time, so this is 8:30 Chicago time. And we do this for 2-minute and 1-minute returns. So, and then we get 30,000 or nearly 70,000 observations respectively. So what is included? Well, in order to parameterize the mean, basically we interact time dummy. So what is a time dummy? Basically we're just looking on 2-minute returns before the announcement, directly at the announcement, and then a few intervals after the announcement. So these are our time dummies, and then we interact this with the magnitude, the sign of the surprises, and the precision. In order to study, okay, what is the direct effect on the conditional mean. The variance regressors must be much more flexible because, well, the effect on the mean lasts only over a very short interval, basically 2 minutes. Yeah? So we just see a jump in prices, the market is extremely efficient, it jumps immediately, and then basically it's gone, yeah, on the mean. But the variance effects, they are much more long-lasting, and also in the variance particular before the announcement, and it's most interesting for us what happens before such an announcement, because it is scheduled, we know exactly when it will come. So the crucial question, okay, what happens with this volatility before the announcement? So we have to fully parameterize volatility during an announcement day. We have to interact it also with the sign and the precision of the announcement. So we really need a quite flexible approach. So maybe you have other ideas then. So this is a fully parametric approach. So Wolfgang won't like it. But rather the question, what we can later discuss it, is whether there is some reasonable alternative. So we decided to basically to model the deterministic pattern of volatility around the announcement, so before and after the announcement, so using some flexible Fourier form, which is of course with a fixed Q, so it's not really semi-parametric, but maybe has some taste of semi-parametrics here. And we interact this with the precision dummies and sign dummies and the magnitudes of surprises. So we generated a lot of regressors in order to capture these interactions. And as we will see in the results, we need it basically. Okay, I do not want to, so this is an ugly table, small figures, and this is also not too important. This is basically what is most interesting. So these phi A, phi B, phi M, so these are the diagonal elements of the matrix, the autoregressive matrix in our state space system. So we see, and this makes totally sense, so the noise, so the autoregressive effect here in the noise components is highly statistically significant, and it's negative. Well, this is basically what we see here. This is the bid-ask bounce effect. So that it jumps up and down the revisions in quotes. Yeah, so this is what we would expect. What we would expect for the autoregressive parameter in the efficient return, well, we would expect that it should be 0. Yeah, then it would mean that there is absolutely no predictability in efficient return. Actually, we see there is some slight predictability. Yeah? So it's highly statistically significant, but this is also, we have a high number of observations. It's very small. Okay, so we can controversially discuss it, what it actually means, but it's slightly negative. Okay, so this is also, later on I will show you the plots. It's much more nice. So don't forget these different specifications, and what you see in this figure here, these are the results for the conditional mean and the ask returns. And what you see here, these are the interactions. So this NF stands for non-farm payrolls, and -2 means, okay, this is the interval directly before the announcement when we see a positive announcement, correspondingly for negative announcements. So this is directly the announcement interval, so 1430 to 1432, the 2-minute interval is directly after the announcement. And, well, this is the next interval, yeah? Okay, and then we have a lot of interactions. But that is not too important. What is most important is, okay, we see this high number here, highly statistically significant, and we see, okay, prices react immediately in the interval when the announcement comes on the market. This is not surprisingly because we know that these announcements, they are published under very strict lockup conditions. Yeah? So it's not anecdotal evidence, or it's the fact that journalists and any reporters, they are really locked up in a room immediately before 8:30 in the US. That means any outside connections are cut. And exactly at 8:30, the news comes on the market, because it is known that it has such a fundamental impact. So it's very important to have these strict locked up conditions. So directly after 8:30, it comes on the market. So here we really know at 8:30 information comes. So it's an ideal, in some sense, a nice situation where we can study the effect of news arrival. So we see, okay, markets react immediately, and then already in the next interval from the 32 to 34, the next 2-minute interval, basically it's gone. Yeah, it's over. Good. Okay, this is not new results, so this has been shown already by many other studies. So what is more interesting for us is, okay, yeah, so for the bit, on the bit side it looks very similar. So now let's have a look on the volatility, yeah, which is most interesting for us. Okay, so what do we see on this picture here? What is on this axis? So these are the minutes. These are the minutes before the announcement. Yeah? So this is directly at the announcement. So minus 400 minutes. Well, this is the start of the trading day. And, well, this is the end of the trading day. I think it ends at 150 or 180, something like that. And this is 2:30. Yeah? Okay, and you see here a solid line and you see a dotted line. The solid line is related to precise news, and the dotted line imprecise news. And further on here, the figure in the top is related to positive announcements, so a positive non-farm payroll figure, which is actually bad news for the Bund future, because of the negative relation. We saw in this figure here, we saw a negative sign. So actually this means bad news in the sense that prices go down. Yeah? And this is correspondingly for positive news where the non-farm payroll surprise is negative. Yeah? Okay, so first of all, what do we see? We see before the announcement there is not much happening here in the ask noise volatility. And this is a plot for a surprise of the magnitude of 20% quantile of absolute surprises. So this is a moderate, rather small surprise. Yeah? So, okay, we see a sharp drop of the ask noise volatility directly at the announcement, and then it quite persists on a level basically until the end of the trading day. We see some slight difference that, for instance, for negative news here, we have a sharp peak here, and then basically it goes down. So we have some asymmetry between positive and bad news, and we will see this much more. This will be much more evident on the next slide. So there's some asymmetry between positive and negative news, which is well known in the literature. So we also see that for precise news, the noise activity, that means quoting activities around the efficient price, is much higher when the news is perceived to be precise. Yeah? And we see this on the ask side, and we also see this correspondingly. Okay, bid side will come later. First of all, now we see basically exactly the same picture. So, okay, maybe I can jump here from here to here. So now for 50% quantile, so this is, say, a median surprise. Yeah? So now we see, okay, now we have it's still relatively stable before. Now it peaks heavily, and then it goes down. So really, volatility jumps up. It jumps up severely. We still have a fundamental difference between precise and imprecise with respect to the precision of news. Okay, and then even more extreme when we go up to the 80% quantile. So this is a big surprise. Yeah? So a big positive and a big negative surprise. So we really see, okay, here the ask noise volatility, it jumps up. Okay, so that means this reflects the quoting activities around the efficient return. And when I say, okay, quoting activity, well, this is an electronic market. That means when quotes go up and down around the efficient return, then this must be reflected to liquidity. Yeah? So that means some people post some new quotes, some people perform some asks and some buys and sells. When the liquidity is low in the market, that means, okay, the prices, they jump up on the ask side or down on the bid side. This is what we see here. So on the bid side, it's exactly the same. You see here I have a lot of figures, so I was not able to produce a film like Wolfgang, so I decided to put a lot of figures here in this presentation. And when I show you, I don't know, maybe 10 figures per second, then it looks like a film. So on the bid side, it's exactly the same. So what happens with the efficient return volatility? Basically nothing before a small surprise. Then it jumps up and it keeps persistent. what is quite surprising here in this point is that for precise news, volatility, the informational volatility is higher. So what is the informational volatility? Yeah? So this is volatility which we interpret, well, this is related to the efficient return, which reflects market participants' uncertainty. Yeah? So differences of opinions what the true price could be. So this reflects volatility in the efficient return. So it is higher for precise news than for imprecise news, which is somehow surprising at this stage. So we will come back to that. Okay, we see again the same picture for median and for high surprises. Then we see in the informational volatility, it really peaks. It really jumps up much more fundamentally than the quoting activities. So, okay, these same pictures are then correspondingly reflected in the finally in the ask return volatility, which is the sum of both. So this is not surprising to see that. So the question is now, and this is most interesting for us, what happens with the proportion of noise to the efficient return? So basically here in this picture we saw, okay, it looks more or less the same. Whether we look on the efficient, the informational volatility, or on the noise volatility, they all behave relatively similar. So the fundamental question is, do they move in locksteps? Does the proportion of noise relative to the informational volatility, does this change around these announcements? Yeah? So, and this is what you see here in this figure. So this is the proportion of the ask noise and the total ask variance before a low surprise. Yeah? So same setting as before. So we see the proportion. So overall, first for a small surprise, it's relatively small. Right? So it's 8%. That means 92% of this ratio is related to informational volatility. Yeah? So the quoting activities are relatively low when we have only when we expect to see only a small surprise on the market. Yeah? What is striking that at the point of the announcement, it jumps down. It jumps down in the sense that the proportion of noise is close to zero. That means most volatility we see after the announcement is driven by volatility of the efficient return, which is information driven, which is informational volatility in the sense that market participants, well, they are not sure but what is the true reaction, so differences in opinion. Okay, we see this much more striking for median and even for large surprises. Yeah? So we see now the fraction here goes up to basically 25%. So there is a lot of quoting activity going on before an announcement when we expect to see a high surprise on the market. Yeah? So that means until around 1.5 hours, so 90 minutes before the announcement, a lot of quoting activity takes place. A fundamental part of the volatility is driven due to quoting activity, and then it jumps down. After the announcement, so it's extreme. After the announcement, all the volatility is basically driven by volatility of the efficient return. Yeah? Okay, so we see this for ask. We see this on the ask side, on the bid side, and okay, I come close. I'm basically finished. We also can look on the ratio between the ask and the bid side. What we generally see, I think this figure is the most interesting in this context. So this is the ratio between the ask and the bid variance. So we see generally higher activity on the ask side than on the bid side. We have to check whether this is representative, but it is the longest sample we can get. Yeah? So we also have to look maybe for non-announcement days, whether this is generally true. And we see, okay, on the ask side is particularly more active than the bid side when we expect to see bad news. Bad news in the sense of a positive new non-farm payroll, which creates a sharp downward movement of the price. Then the ask side is much more active than the bid side. Okay, good. Okay, so I skipped that. So these are basically the estimations of the Arch1 dynamics and also the mutual correlations here. And I come to the, okay, I can just summarize with respect to the variance effect. So what we see that large surprises really induce jumps in both noise and information volatility, first of all, which is not surprising. Yeah? But the proportion of noisy volatility before announcement rises with the revealed surprise, with the magnitude of the real surprise. Yeah? This is quite interesting, and the significant reduction of noisy volatility after announcement is the most striking result, that we really see, okay, there are a lot of liquidity-induced effects before the announcement, but not after the announcement. Yeah? Then basically all the movements we see is really due to movements in the underlying efficient price. Yeah? So with respect to the precise versus imprecise news, imprecise information generally reduces all volatility components. And we see also that the effect on these proportions basically depends on the news sign and the magnitude. So we have quite complex interactions between these different variables. Therefore, we need a relatively highly parameterized model in the variances. Yeah? And finally, the large, the precise, bad surprises. So this is the worst case. Yeah? So, and this, of course, not surprisingly, effectively creates the strongest noise. Okay, thank you. No, this will be the next step, yeah, because...
I was wondering whether the volatility might just be related to everybody's waiting for this information
Exactly.
and then they trade, and you will have a single market before.
Yes, exactly. So this is basically somehow also captured by these noise components, and it would be interesting also to control for volume. So we have volume. This is also the reason why we took this data, in order to be able to control for volume. Yes, that would be the next step, but it didn't so far.